Today we're going to talk about sequences. A sequence is an ordered list of numbers. Sequences are discrete and not continuous, and to write an equation that represents a sequence, or a rule, instead of y equals, we use a subscript n. We also use subscript to describe which term we're talking about. So the subscript n represents the term's place in the order of that sequence. For example, a sub 1 is the first term. Find the following given the sequence 2, 6, 18, 54, 162, 486, and so on. 2 is a sub 1, the first term that has been given. 6 is a sub 2. 18 is a sub 3. 54 is a sub 4, the fourth term. 162 is a sub 5, the fifth term. And 486 is a subscript 6, the sixth term. So when filling in the following, a sub 1 is 2. A sub 3 is 18. However, they didn't give us a sub 0 or a sub 10. So what term would come before the 2? Well, let's look at the pattern that this sequence follows. Each term is being multiplied by a common multiplier or a common ratio. That common ratio is 3. So if I wanted to know what happens before 2, I'd be asking myself what multiplies by 3 to get 2? Or I would take 2 and divide 3. To get the 10th term, let's find the next 4 terms in the sequence. So if you keep multiplying by 3, you'll get 1,458, 4,374, and so on. Our 10th term then would be 39,366. And I did not initially write the commas in those numbers to not confuse us with the fact that a sequence is written with commas in between each number. Recursive sequence notation. To write a recursive rule for a sequence, we refer to given terms, making it so that the only way to find a certain term in the sequence is to write out that entire list. But an explicit rule gives you a rule that you could plug in any value of n and get the desired term. Some notation would be a subscript n minus 1 is talking about the term that comes right before a subscript n. A sub n plus 1 comes right after a sub n. N has to be an integer greater than 0. A sub n minus 2 is the term before a sub n. And similarly, a sub n plus 2 would be the term after a sub n. So the subscript is only giving you the order of where these terms lie. Given the sequence that we had in the first part, if I'm referring to the term 54 as a sub n, then what term is a sub n minus 1? Well, a sub n minus 1 is the term before. The term before 54 is 18. If I'm referring to 6 as a sub n, what is a sub n minus 2? Well, a sub n minus 2 would be the term before. So remember, 6 is a sub 2. So the n we're referring to is 2. If you plugged that in to find a sub n minus 2, so a sub 2 minus 2, you would get a sub 0. So what's a sub 0? 2/3. Subscript helps you organize a sequence based on its order. State whether the sequence is arithmetic or geometric. Identify the rule as explicit or recursive. Find the first 5 terms and the term indicated. In class, we did an introduction that referred to sequences as arithmetic or geometric. Remember that arithmetic sequences have a common difference and appear linear, and geometric sequences have a common ratio and appear exponential. Here's the form for writing an explicit rule for an arithmetic sequence and a geometric sequence. For 1a, first we have a sub n, which is basically y, and it's dependent on your independent n. This to me looks like y equals b plus mx, your independent variable and your dependent. And b, or -2, is just my y-intercept, or a sub 0 in this case. This will appear linear, which means it is an arithmetic sequence. I have a rule, a sub n, dependent on n. That is an explicit rule because I can plug in any value of n and find that indicated term. So find the 23rd term by plugging in 23 for n. So a sub 23 is 182. For part B, I clearly have multiplication. This looks a lot like an exponential function, which means we have a geometric sequence. Again, a sub n is written as a function of n, so we have an explicit rule. To find a sub 9, plug in 9 for n. So a sub 9 is 512 for this geometric sequence. Part C has given us a sub n as a function of term before. When your rule relies on existing terms or the term before in order to create the next term, you have a recursive rule. I cannot just plug in 20 and get the answer. I have to find the first 19 terms in order to get the 20th term. So let's see what kind of sequence we have. The very first term is negative 31. To find a sub 2, plug in 2 for n. A sub 2 minus 1 is just a sub 1. What was a sub 1? Negative 31. A sub 3? So we can see how subscript works to help us organize and figure out our terms. But let's write these out and see if we can see a pattern that's happening. Oh wait, this recursive rule just means to find the next term, take the term before and add 6. So I'm just going to keep adding 6 to get the next few terms. Notice how we were adding 6 every time. That is a common difference. So this rule represents an arithmetic sequence. For part D, we're taking the term before and multiplying by 3. That's going to give you a geometric sequence. And it's dependent on the term before, so it's a recursive rule. A sub 2 means I'm going to take the term before and multiply by 3. Keep multiplying by 3. So a sub 9 is 19,683. When you see a list of numbers, unless otherwise stated, the first term is a sub 1. So we want a rule that uses a sub 1. That means our formula just looks slightly adjusted from y equals mx plus b or y equals ab to the x, because the formulas are based on knowing what a sub 1 is. It's much more common to know a sub 1 than a sub 0. Write the explicit rule for each arithmetic sequence given 2 terms. When n is equal to 14, a sub n is 77. That's the point 1477. This one is the point 34 to 17. To find an arithmetic sequence, we simply want to know the equation of the line that would connect these points. Obviously, a sequence is not connected, but what equation would connect these points? Let me first show you how to use the formula, and then we'll check it with what we already know about linear functions. Plug in 14 for n. Plug in 34. All right, let's plug in what is a sub 14? It is 77. And what is a sub 34? It's 217. And then we're going to have 2 equations with the same 2 variables, and we can use elimination or substitution to solve. Now let's plug in the first term and the common difference into our formula and simplify. Go ahead and distribute d in order to get your rule. So here's our explicit rule. You have to distribute that common difference. If you do not distribute it in, then you haven't simplified the rule enough. Now, what would happen if we had just found the equation of the line that went through these 2 points, 1477 and 34217? Let's go ahead and do that and see if we get the same answer. And wow, look at that. We got the same equation. This one's just in y equals mx plus b form. This one is our arithmetic sequence explicit rule simplified. You can go ahead and try number 2 on your own and then press play when you're ready to check. So now we have our common difference and our first term, a sub 1. Go ahead and plug it into the explicit rule formula, distribute the common difference, and simplify. The explicit rule for this arithmetic sequence is a sub n equals negative 15 minus 4n. For number 3, we're going to write the explicit rule for each geometric sequence. For geometric sequences, we'll have 2 equations with the same 2 missing variables. This time we will have to use substitution. Elimination is not an option because geometric only deals with products. So use substitution to solve. Now that we know r is negative 6, go ahead and plug it in. We'll use this equation and solve for a sub 1. Then you can plug it in and write your explicit rule. There will be no more simplification needed after you plug it in for the final rule. That makes our explicit geometric rule a sub n equals negative 3 times negative 6 to the n minus 1. When it came to an exponential function, the base of your exponent cannot be negative. When it comes to a sequence, it can definitely be negative. That means you have terms that alternate signs. Use the same process we did in part A to try part B. Press play when you're ready to check. Here is our final explicit rule for this geometric sequence. And that's sequences.